Hi there and welcome to the video on dividing polynomials. The skill objectives for this particular video are 1, to divide polynomials using long division, so we'll review that. Divide polynomials using synthetic division, so we'll be looking at that as well. I know both of those are reviewed. We are going to look at identifying all possible rational zeros, and we'll talk a little bit more about what that means. And our conceptual objectives are extend to long division to polynomials and understand when synthetic division can and cannot be used. Before we get to actually doing the division, let's talk about this thing called the division algorithm. The division algorithm really tells us what a division problem is. So what we're going to have is if we take two functions, one is p of x and the other is d of x, are polynomials, and d of x does not equal 0. Okay, and the degree of p of x is greater than or equal to the degree of d of x. Then there are unique polynomials q of x and r of x such that p of x is equal to d of x times q of x plus r of x. In other words, p of x is our main function, d of x is what we're dividing by, q of x is the quotient, and r of x is the remainder. So what we're saying here with the division algorithm is if I take p of x and divide it by d of x, I'm going to get some quotient and I can add that remainder. Now if r of x equals 0, then we say d of x divides p of x, and d of x and q of x would be considered factors of p of x. Pause the video right now, look that over again, make sure this gets written down. Start if you have questions, because we will talk about this in class as well. This division algorithm is what we're going to use to allow us to place meaning on some of the problems that we're going to be doing in this section and in the sections to come. One other thing though, another way to look at this is that if I take p of x divided by d of x, that is going to be q of x plus r of x over d of x. In other words, I want you to think back to when you did long division problems back in middle school. We're going to see an example of that again in a second, but remember when you did that, one of the things that they often had you do is you wrote down, when you did the division, you wrote down what the quotient was, and then you had the remainder over whatever you were dividing by, what that divisor is. And that's really what we're looking at here, except now we're dealing with polynomial notation. Let's kind of recall how this whole division problem worked. Let's go back to elementary school when we took something like 14 going into 327. Well, the first thing you did is you looked at how many times did 14 go into 32. And we would say, well, 14 goes into 32 twice. So we put a 2 above the 2 in the 327, and then we multiplied 2 times 14. And that gave us a 28. So we had 28 there. And then what we did is we subtracted. And when I subtracted, I would get, in this case, 4. And then I would have to bring down the 7. And then the whole process would start over again. I'd say, well, how many times does 14 go into 47? And we'd look at that and we'd say, well, that's going to be 3 times. And 14 times 3 does come out to be 42. So I put the 42 there. And then we would subtract. And the final result on that, when I took 47 minus 42, I got 5. So in this case, when I take 327 divided by 14, I get 23 with a remainder of 5. Or we could sit there and say that the answer was 23 and 5 over 14, and 5/14. So that was often how we went through and worked with these problems back in elementary school. Let's take a look at a long division problem involving a polynomial. In this case, what we're going to start out with is an example. We're going to take 12x cubed plus 2 plus 11x plus 20x squared, and we're going to divide it by 2x plus 1. Now the first thing I want you to notice here is that this polynomial, our p of x here, if you will, that is not in proper order. It's not in that descending order. So whenever we do a long division, we're going to want to go through and make sure we're in that descending order. So like in this case, we have a third degree polynomial. So it's going to be third degree, then our second degree term, first degree term, and then constant. Also, if you happen to notice, this one doesn't have that, but if you happen to notice that a term is missing, maybe I don't have the 11x. Maybe it's just 12x cubed plus 2 plus 20x squared. Well, when I write that into this notation, I would want to put a 0. I want to make sure I have my placeholders in there. This often, it's there to make sure everything stays organized, and you don't have, and to eliminate problems. I've seen people, it's not a life or death thing in terms of the problem if you don't do it, but I've seen people make a lot of mistakes by not putting in those placeholders when they are needed. So please try to remember to put the placeholder in when you see a missing power of x. So the way this long division works when you're working with polynomials, what you're going to do, I want you to start out, you notice the 2x here and the 12x cubed. And what you want to ask yourself is, what do I have to multiply 2x by to make it look exactly like 12x cubed? Well, the answer on that is 6x squared. So what we're going to do is somewhere above, and it doesn't really make a difference where, I'm going to put a 6x squared. Now, like we did with the long division we did before, we're going to now take that 6x squared and we're going to multiply it by everything here. So I'm going to take 6x squared times 2x and then 6x squared times the 1. And when I do that, for this particular problem, I am going to get, I will get 12x cubed plus 1 times 6x squared is going to be 6x squared. And what I'm now going to do with that is I'm going to go and subtract it. Now when I subtract this, it means I'm going to have to change all of my signs. All the signs in this part that I have here in blue are going to be changed. So I'm going to subtract and subtract that one. And when I do that, when I simplify that, the 12x cubed minus 12x cubed is going to be 0. 20x squared minus 6x squared is going to be 14x squared. And then I'll bring down plus 11x. And I tend to just bring down everything, so plus 2. It's up to you. You can bring down one term at a time, but there are times later on where you might need to actually bring down more. So I tend to just bring everything down. It's not going to make a difference either way if you choose not to, and it's not going to cause a problem for you in terms of on a test or quiz if you choose not to either. Now, what happens now is at this point, we start out this whole problem exactly the same way what we just did. We take the 2x squared, and I have to ask myself, what do I have to do to 2x squared to make it look exactly like 14x squared? So what do I have to do to 2x, to make it look like 14x squared? Well, the answer on that is I have to multiply it by 7x. So I'm just going to put plus 7x up here. And when I multiply 7x times the 2x plus 1, I am going to get 14x squared plus 7x. And then, like we did before, I will now subtract everything. And when I go through and do the subtraction, 14x squared minus 14x squared, that drops out. 11x plus 7x, or plus a negative 7x, is going to be 4x, and the 2 comes down. And the next thing I have to do now is do the whole thing again. What do I have to multiply the 2x by to make it look like 4x? Well, the answer on that is going to be 2. So I will put a plus 2 up here. And then when I take 2 times the 2x plus 1, I will get 4x plus 2. And again, change all the signs. Everything's going to become negative here. Be aware that if we were dividing by a subtraction, that sometimes it might have to make it into a positive. And so this is going to come out to be a remainder of 0. So in this case, 2x plus 1 and 6x squared plus 7x plus 2 are factors of 12x cubed plus 20x squared plus 11x plus 2. So I know in this case that my answer, my quotient in this case, is 6x squared plus 7x plus 2. And I have a remainder of 0 on this one. Now let's look at synthetic division. Synthetic division is really a shorthand method for dividing a linear factor in the form of x minus a or x plus a. Let's look at an example here because it's really the key in how we set this up. The nice thing about synthetic division is we're not going to see any x's. We just deal with numbers. And so when we look at a synthetic division problem, one of the things you're going to notice is you're going to see a row of numbers. You'll see it set up like this. There'll be a line like this. And what you're going to notice here in this location right here, we're going to see the coefficients of our dividend, of this polynomial that we're dividing. So in this case, and you want them in order, and so it is going to be a 3 here, then a 1. Notice there's no x squared, so I want to put a 0 in for the x squared. I'll put a 2 and then a negative 3. The next thing I have to do is what I'm going to actually go and put into this thing. In this case, we're looking at the x plus 2. Remember, we're in that form. So in this case, on this problem, we're going to go through, and since we're dividing by x plus 2, we're going to put right here a negative 2. It's always going to use the opposite sign of what you see in the problem. So if I have an x plus 2, I'll put a negative. If it was an x minus 2, I would have a positive 2 there. Now the way synthetic division works, the nice thing about it is that we go through on this, and it really just involves addition and multiplication, the two operations that tend to be easiest for people to do. So the first thing I'm going to do is the very first entry, the very first coefficient I have in the in blue there, the 3, that is just going to be brought down, and I'm going to put the 3 right there. And what I'm going to do now is I'm going to take the negative 2 times the 3. Well, negative 2 times 3 gives me negative 6. And then I'm going to add the 1 and the negative 6 to give me negative 5. Now I'll take the negative 2 times the negative 5, which gives me positive 10. I add the 0 and the 10. I get 10. Negative 2 times 10 gives me negative 20. And when I add the 2, I get negative 18. And the last thing I have to do is take negative 2 times negative 18, which will be positive 36. And when I add it, I get 33. Now, what we have here at the end, this one at the end, that's our remainder. Now, these numbers here form the coefficients of the quotient. So in this case, we start out with, it's always going to be, the quotient is always going to be 1 degree below what we started with. So in this case, we started out with a 4th degree polynomial here. So when we do synthetic division, this result is going to be a 3rd degree. And the answer on this one is that we are going to get, since it's a 3rd degree, it will be 3x cubed minus 5x squared plus 10x minus 18. And now the remainder is 33. So it's going to be plus 33 over the x plus 2. So this would be our quotient right here. And then we do have our remainder right here. And it's always going to be over the x plus 2. Let's look at another example. In this case, we're going to take x to the 4th minus 81, and we're dividing it by x minus 3. Well, when I set this one up using synthetic division, I'm going to start out, I draw this here, that sideways L, if you will. And I'm going to put the coefficients for the dividend, the top, the x to the 4th minus 81, across in this across the top here. Now, what I want you also to notice on this one is that we don't have an x cubed, x squared, or x term. So we're going to have we're going to have some some placeholder zeros, and you absolutely must put those zeros in there. A synthetic division problem will not work out correctly if you do not put the zeros in their spot. So in this case, when I set it up, I will have a 1 for 1x to the fourth. I have 0x cubed. I have 0x squared, I have 0 x's, and then I have the negative 81. And the number that's going in this spot on the other side of the vertical line is going to be, since we're dividing by x minus 3, that's going to be a 3. So now I'm all set to do the synthetic division. So what I'm going to do, the first thing is that 1, my first term, that just comes down, and I put that right there. That's going to be the first coefficient in my quotient as well. And then I take 3 times 1, I get 3. And when I add it, I get 3 there. 0 plus 3 is 3. Then 3 times 3 gives me 9. 0 plus 9 is 9. 3 times 3 is 27. Add it up, I get 27. And 3 times 27 is 81, and when I add it, I get 0. So in this case, we do have another instance where the divisor went into the dividend evenly. So we know that, number 1, our resultant, our quotient polynomial, is going to be x cubed plus 3x squared plus 9x plus 27. And that is a factor of x to the fourth minus 81 as well as x minus 3. So our final answer on this one, though, is just that polynomial because our remainder came out to be 0. The last thing we really need to look at today is going to be what's called the rational zero theorem. Now, why do we want to look at rational zeros? Rational zeros are the ones that are really the nicer ones. These are the ones that are integers, rational zeros. Any rational number can be written as a fraction involving an integer numerator and an integer denominator. In other words, the top and the bottom would be integers. So therefore, making it easier to work with. So, if a polynomial function, p of x equal to a sub n x to the n plus a sub n x to the n minus 1 plus the dot 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0. If that is a has there, has integer coefficients, then every rational zero of p of x has the form where the rational zero is going to be an integer factor of a sub 0 over an integer factor of a sub n. In other words, it's going to be plus or minus the positive integer factors of the constant term over the positive integer factors of the leading coefficient. Now what we're going to ask you to do is we're just going to ask you to list off the possible rational zeros. The nice thing about this will give us a list of all the possible nice zeros, nice numbers that could be zeros for our when we're looking at a polynomial. So let's look at an example next. In our example, we want to list off the possible rational zeros for 3x to the fifth plus 2x to the fourth minus 5x cubed plus x minus 10. Well, in this case, we know from the theorem that our rational zeros are going to have to come, you should actually say the possible rational zero, are going to have to be in the form plus or minus where we have our integer factors of our constant term, which in this case is negative 10. While the integer factors for 10 are going to be 1, 2, 5, and 10. Over the integer factors of our leading coefficient. Well, our leading coefficient this time is 3, so those integer factors for 3 are going to be 1 and 3. And so when I start listing off my possible rational zeros, It's going to be everything in the numerator over everything in the denominator. So my first set, in this case, I would have 1 over 1. I'd have plus or minus 1 over 1, which would be 1, plus or minus 2 over 1, which is 2, plus or minus 5 over 1, which will be 5, and plus or minus 10 over 1, which would be 10. So that would be my first set. After that, I'd have another set. I'd have to do plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 5 over 3, and plus or minus 10 over 3. So for this particular polynomial, if I do have any rational zeros, they would have to come from this list. This now will end the video that we have for doing the division with polynomials and looking at this rational zero test. I'm going to ask you to do just a couple things here. I would like you right now, in terms of finish this up, I would like you to do 2 more synthetic division problems. I want you to do these 2 problems here, the x to the 4th minus 7x cubed plus 5x squared plus 9x plus 5 divided by x minus 2, and do x squared plus 9x minus 4 divided by x plus 5. What I'd like you to do with those is first I want you to go and do the synthetic division, identify the quotient, and identify what the remainder is. Then what I would like you to do after that, I would like you to go and take positive 2 for this first problem. I'd like you to put positive 2 in for x. Just take the positive 2, put that in for x into this problem here, and tell me what you get. Look at what you get. See if you see something similar to what you in terms of what you did for the synthetic division. And by the same token, I'd like you to go through and put a negative 5 in for x into this problem. And again, see what you get. Compare it to what you came up with when you did the synthetic division. Identify what you may have noticed and bring it to class next time. So with that, have a good evening, and we'll see you in class.